Thanks for joining. We're about to do some practice problems, which is one of the best ways that we have to help us learn. Now, if you haven't tried these problems yourself, please try them yourself first. There's this beautiful button. It's somewhere along here called pause. Make use of it. See the problem? Pause. Try it yourself. Then if you need to, you can unpause and we can compare answers. In this way, you get engaged, you'll learn, you'll succeed. And that's what we want, your success. Let's get going. Find A and B such that the points P314, Q55 minus 2, and RAB10 are collinear. Let's talk a little bit about notation here. When it says P314, it's not like we're trying to plug 314 into some function. It just means we're going to call a point P, and these are its corresponding coordinates. We're going to call a point Q, these are the corresponding coordinates. Point R, these are the corresponding coordinates. There's one other thing we need to talk about. We have this word collinear. Okay, so let's talk about it. Well, there's two pieces, the co, and that means together. So they're all together. Well, what does that mean? There's the second part, linear. And that refers to a line. Collinear means that these 3 points all share a common line. They all have something in common. All right, so let's think about what the picture is. And right now, we don't have to worry about being super precise with the picture. We're working on intuition. Intuition is the important part here. So we have our space. So we'll draw our three-dimensional space here. And now we'll start by saying, well, we have points P and Q happening to be somewhere. So we'll mark P and Q. Let's say we put P here, and let's say we put Q here. We're collinear. Now it turns out if you have 2 points, you can make a line. So we say, all right, let's draw that line that connects those 2 points. And so we have a line. There we go. There's that line. And we're told, hey, R is somewhere on this line. So we say, okay, well, let's just put it somewhere. Maybe we'll put it here. Now, does it go there? I don't know. But for right now, we're worried about the intuition. All right, so now we have our picture. What can we do? Well, we can certainly put down the corresponding coordinates. So we can say P, that's 3, 1, 4. Q, 5, 5, minus 2, and R, A, B, 10. And, well, we sit here and say, what do we have? We haven't learned too much. We've learned about coordinate systems. Okay, what else have we learned about? Vectors. Well, I don't know if there's much we can do with coordinate systems, so maybe vectors can be useful. And we say, well, let's think about what's going on. When you have points, it's natural to make vectors. So we say, well, there's this vector, P over to Q, and that's a vector we can find. There's another vector, P over to R, we can kind of find it, involves A and B. But what do you see about these 2 vectors? Both of them can be put down into that line. Well, if they both go into that line, then that says, oh, they're both pointing along that line. In other words, these are parallel. Now, I'm putting parallel here in quotes because there's a subtlety. What does parallel really mean? It means that they're scalar multiples of each other. Okay, so here's our idea. Let's write down these 2 vectors. So we have the vector P to Q. And to find that, we say, all right, let's look at the change. And notice that when we wrote down points, we used our parentheses. And when we're going to write down vectors, we're going to use our angled brackets, the ones with the sharp corners. So we say, okay, P to Q, I went up by 2 in the X, up by 4 in the Y, and then, big change, down by 6, right? 4 went to negative 2. I went down by 6, minus 6. Now, similar thing, P to R. What happened here? Well, I went from 3 to A. Well, that's not so bad. We just write down the difference. A minus 3. Where you stop, subtract where you start. Then the next coordinate, B minus 1. And our last coordinate, 10 minus 4, is 6. All right, so those are our two vectors. Now, we said that they're parallel, and that's the key idea. That's going to be what helps us solve this problem. Parallel vectors means that they're scalars of each other. So, we know the following. Now, since parallel, we'll make a little note here for ourselves. Since parallel, we know that this vector P times Q is some multiple of P to R. I said P times Q, P to Q. And, okay, well, what does that tell us? Well, it tells us that 2 for negative 6 is some multiple A minus 3, B minus 1, 6. And you can move that scaling factor in. So that's T A minus 3, T B minus 1, and 6 times T. Okay, so we have these two vectors. What's true about vectors? Well, vectors are the same. Let's see, that's what equals means, same, if and only if they're the same in each coordinate. So you say, okay, now we'll do our matching game. Say things such as, well, the 2 has to match up with this T times A minus 3. All right, so 2 is equal to T times A minus 3. The 4, that has to match up with the T times B minus 1. And the minus 6 has to match up with the 6T. And now we have 3 equations, 3 unknowns. But I don't think it's going to be too bad, because look at that last equation. Minus 6 equals 6T. Well, hey, that tells us T has to be negative 1. Okay, so we can put that into our other 2 equations. And so, for instance, this says 2 equals minus 1. And I can distribute the minus through. So minus A plus 3. And here, this becomes 4. And again, distribute that minus through, equals minus B plus 1. And now we can just move things around. Move the A across, move the 2 across. And we get A equals 1. And, right, because A, 3 subtract 2 is 1. Here we get B is 1 minus 4. So B is negative 3. And we're done, right? Because what did we want? You should always remember, what does the problem ask us to find? It says find A and B. We found A and B. They're right there. And so we put a nice little box around it, and we've succeeded. All right. Now, if you're wondering, like, wow, are we going to do a lot more with lines? And the answer is yes, we're going to do a lot more with lines. Because lines are a flat thing. And if it's one thing that we love in calculus, we definitely love flat things. So lots more good line stuff still to come. Find a spherical coordinate equation for the plane given in rectangular coordinates by z equals 2x plus 3y minus 5. Give your answer in the from. Ha! Typo. Classic people not proofreading. That's okay. We know what they meant. Form. You know, they're math people. We forgive them. So in the form, rho equals f phi comma theta. And what does that mean? Well, it means solve it for rho. So we're going to say, all right, let's put things in terms of rho. So how do we do this? Well, we're going to look and say, well, there's a collection of formulas that help us translate from one coordinate system to another coordinate system. Now, if you're a believer in the formula sheet, and who isn't, you'll notice that there's a couple of handy formulas to refer to. So let's write those down. We have the following. We have that z is rho cosine phi, and r is rho sine phi. Now, that's useful here because this is z. Perfect. That lets us replace the z in terms of spherical coordinates. But we need to get x and y too. Now, those aren't explicitly in the formula sheet, but they're in there implicitly because there's another set of equations. And that is x is r cosine theta and y is r sine theta. Now, these are usually thought of as polar coordinate formulas, but what we can do is say, look, we've got an r formula. Here's r. So now replace those r's. So we get the following. We get that x, that's rho sine phi cosine theta, and y, that's rho sine phi sine theta. So we now have z, x, and y all written in terms of spherical coordinates. So that's most of the game. From here, what do? Well, we substitute in. We say, what is z? Z is rho cosine phi. So rho cosine phi equals 2. What is x? Rho sine phi cosine theta. Plus 3, what's y? Rho sine phi sine theta. And minus 5, which in spherical coordinates is written as minus 5. Yeah, there's nothing to change. Minus 5 is minus 5, right? The only thing we're doing is we're changing what we used as coordinates. X, y, and z be rewritten in terms of rho, phi, and theta. Okay, so just to help us follow along what we did, we'll make some notes here. This is our z. This is our x. This is our y. Now, are we done? Not quite. We have rewritten it in terms of spherical coordinates. Yay us. However, there were additional instructions. The additional instruction says, give your answer in the form rho equals something involving phi and theta. So we need to finish it up. We need to solve it for that rho. So here's what we can do. Everything that has a rho, we'll put on one side. So let's move these pieces across. Everything without a rho onto the other side. So we're going to leave that minus 5 there. So if we do that, we get rho cosine phi minus 2 rho sine phi cosine theta minus 3 rho sine phi sine theta equals negative 5. Now, we put all the rho's on one side, so everything on this side has a rho in common, which means we can pull it out. So rho times cosine phi minus 2 sine phi cosine theta minus 3 sine phi sine theta equals negative 5. And now we're in our happy place. We have one rho to row them all, right? What's the last thing we need to do? We have to get rho by itself. So we move this across by division, giving us that rho is equal to a fraction. We have the negative 5 upstairs, and downstairs we have all these pieces. The cosine phi minus 2 sine phi cosine theta minus 3 sine phi sine theta. And that's the answer. Woohoo! We're done. So this is practice in doing conversion. And so when we're moving from one coordinate system to another coordinate system, if we have an expression involving our old variables, well, old being our original coordinate system, we just have to go through and systematically work out what is that in terms of our new coordinates, and that'll help us find the answer. So a lot of things are just a matter of like rewrite things using our formulas that we have available. And with practice, it'll become second nature. All right, good. Let's keep going. Find the minimum distance from a point on the sphere x minus 3 squared plus y plus 4 squared plus z minus 3 squared equals 64, and a point on the sphere x minus 4 squared plus y squared plus z plus 5 squared equals 400. All right, so let's first think about these spheres. And let's do them both individually. Now remember, spheres have two important things: centers and radiuses. So let's talk about those two aspects for each one of these spheres. So let's start with our first one, x minus 3 squared plus y plus 4 squared plus z minus 3 squared equals 64. Now, 64, we want to think of it in terms of a square. 64 is 8 squared. Okay, equals 8 squared. Now, what does that tell us? Well, when we look at our center, it's x minus our x coordinate of our center. Okay, so that says it's at 3. Y minus something, well, so this should be y minus minus 4, so negative 4, and 3 again. So 3 minus 4, 3. What's our radius? It is 8. All right, now that's our first sphere. Let's do our second sphere, and similar process, we'll write it down. In this case, we didn't have to do any completing the square. They're so nice. I'll tell you, our math teachers, they're the nicest people. It's like they want us to succeed. 400 is 20 squared. Okay, so that's 20 squared. All right, so what do we have? That center is where? Well, x equals 4, y equals 0, and z equals negative 5, and the radius is 20. All right, good, good. Now, there's one more thing before we draw a picture, because I think pictures are helpful to understand what's going on. We understand the centers and the radii. What I want to know is, how do these relate to one another? Okay, in other words, the distance between the centers. And that's going to play a role here. Okay, so distance between centers. What will that be? Well, we're about to find out. It's going to be the square root, and we're going to take from here to there. Okay, so 3 to 4. All right, that's 4 minus 3 squared. Really, it's the change in x squared. Then plus 0 subtract negative 4 squared. Again, what's the change in y squared? And then negative 5 subtract 3 squared. Okay, so if we work this out, what do we get? This is the square root of 4 minus 3 is 1. 1 squared, 1. This is 4. 4 squared, 16. And this is negative 8. Negative 8 squared, same as positive 8 squared, it's 64. And 64 plus 16 is 80, plus 1, oh, that's square root of 81, which means that square root of 81 is 9. Okay, good. Now we almost can see a picture, but I want to point something out. Notice that the distance between the centers is 9, but the radius of the big one is 20. What does that tell us? Well, it tells us sort of how they relate to each other. So in particular, what we can think of is we have our first sphere, well, I should say our big sphere, and that's, I said first one, but I'm really drawing the second one first. So the center is at 4, 0, minus 5, and the radius here is 20. And now, inside that sphere is going to be this other sphere, the smaller sphere. Okay, now what's that going to look like? Well, it's going to be somewhere, and let's say here, and it'll look like this. It has a radius of 8, and it's at 3 minus 4, 3. Now, what's our question? Find the minimum distance. Okay, you know, it's always important to make sure you know what you're looking for, because sometimes you get lost and you might say, well, wait, what was I doing? And you have to think about, okay, what's the picture telling us? Well, how do you find minimum distance? And here's our intuition. You say, well, imagine instead of having the bigger radius go this direction, we went off this way. Our minimum distance is this length right there. All right. Well, that's what we're after. That's as close as they ever get. Now, pro tip, in case I don't say this anywhere else, sort of one intuition about when you know things are probably minimal is that things form a nice right angle. And if you were to zoom in closely here, you'll see that, oh yeah, it's forming a nice right angle with those spheres. And you might also, by the way, be critical of my drawing, saying, Steve, those aren't spheres, they're circles. And I'm like, well, okay, I gotcha. But it's the intuition that we're going for. You know, we could add some little tiny bands around and say, they're spheres. And if it helps, I'll go ahead and do that right now. And so just so you're like, yeah, okay, cool, Steve. Now you're cooking. But the important thing is think about the picture. Now, how do we finish this up? Well, that's what we want. And we just break it into little parts. We know this piece is the radius of the inside circle, the smaller circle. That's 8. We know that this length is the distance between the centers. That's 9. We know this total length, that's the radius of the big, is 20. So 9 plus 8 plus what we're looking for has to equal 20. So 20 has to equal 9 plus 8 plus our min distance. So what's the answer? Well, our answer, move things across. And so we get that the minimum distance is going to be equal to 20 subtract 9 subtract 8, which means our minimum distance is 3. All right, good. Now, I will say that this problem relied on the geometry of what was going on. In other words, one sphere was inside of another. If the spheres had been disjoint, well, we would have thought about it in a slightly different way, but still philosophically the same. If they'd been disjoint spheres, okay, let's think about what that would have meant. For disjoint spheres, what do you do? Let's see. Let's move it over here. Let's think about the picture. If the spheres were disjoint, so here's another case you might encounter. If I have one sphere here and another sphere over here, and I want to say, well, what's the minimum distance? Well, again, think about the line that goes through the center, right? Because ultimately that's what we did, is we said, look at the line going through the center and see how it interacts. So in this other case, what do? Well, you look at the distance between the spheres, and then if you subtract the two radii, then that will give you the distance that you want. So just think about the situation. How do they relate to one another? And so be careful, right? Be the right amount of careful. But of course, that's what we do. We're careful people. Careful, methodical, and we're going to get all these questions. Oh yeah! The surface rho equals 18 cosine phi describes a sphere. Really? Huh. Identify the center and radius of the sphere. Rewrite the equation of the sphere in Cartesian or rectangular and cylindrical coordinates. Okay, so first off, we're told this describes a sphere. Not immediately obvious that it does, but that's okay. We can work on it. We can make progress. We will make progress. Now, there's a couple of clues here. Notice we see the rho, and I'll admit rho does look a lot like a P, and we see phi. When we see those symbols, rho and phi, we say, oh, this is something in spherical coordinates. So what should we do? Well, we should switch into something we're comfortable with. Where are we comfortable? Cartesian coordinates. That's our bee's knees, right? It's our bread and butter. It's what we're used to. So we say, oh, okay, well, let's start working our way to that. Let's try to get into our Cartesian coordinates. Okay, so we start saying, and we look at our formulas that have connections to spherical and Cartesian coordinates. And so, for example, we'll see things such as r equals rho sine phi and z equals rho cosine phi. Those are on our formula sheet. And this one will catch our eye. And we'll say, ooh, that's a nice formula. Why? Because it has a cosine phi. And we're like, brilliant, brilliant. That's the kind of thing we like. And we say, okay, well, what can we do? Well, we know we currently have rho is equal to 18 cosine phi. Whoops, I can spell cosine phi. And we say, what do we want? Well, we want rho cosine phi. We don't have rho cosine phi. So what do? We make it. That's right. If we don't have what we want, we're going to put it in. So how do we get a rho there? Well, the simplest thing is let's just write it. And you might say, are you allowed? Well, kind of. So let's just start by writing down what we want. This is what we want. Now think about how we would have gotten there. We would have gotten there by multiplying by rho, because that's what we did. So we say, okay, as long as we do the same thing to everything, we're okay. So I don't need to multiply the other side by rho, giving us rho squared. And at that point I say, oh, you know what? There's another formula that we didn't write down. It says that rho squared, that's x squared plus y squared plus z squared. Nice. Okay, so here we go. We get the following. We're going to substitute, and I'm going to switch colors because we're switching coordinate systems. And what do we get? We get that x squared plus y squared plus z squared. That's our rho squared is equal to 18z. Okay, we are making great progress here. And let's move things across. So we're going to move the variables together. Now, there's only the x squared, there's only the y squared, but for the z's, I have two pieces, z squared and minus 18z. And I'm going to leave a suspicious gap. And you're like, ooh, well, that's very suspicious of you. Did you do that with good intentions? I did it with great intentions, because we're going to make good use of that gap. Mind the gap. Okay, so what's going to happen here? Well, we're going to do completing the square. Almost always, if you don't have things already squared and you know the sphere is involved, you're going to have to do the complete the square. All right, so that's our goal. We're going to complete the square in this slot. So how do we do that? Well, the method, as a reminder, says, okay, since we have a 1 in the front, take this middle term, which is negative 18. We just want the coefficient. Divide it by 2. That's negative 9. Now square that. And that's what you need to add in. So technically, you could say this is negative 9 squared. That's what we're going to add. And, well, okay, so I can't just add it there. So I'll also add it over here. Now, normally we would write this as just 81. That works too. Okay, now what does all that give us? Well, it gives us the following. X squared plus y squared plus z minus 9 squared, right? Because that's what completing the square does. It makes it a square, is equal to 81. And that says, aha, now we can read off. Our center is at 0, because the x squared means x minus 0 squared, so 0, 0, 9. And our radius is 9. Okay, so that's part of it, right? We've identified the center and radius of the sphere. Check. Now, there's also another part which says, hey, rewrite the equation of the sphere in Cartesian. Well, hey, that's Cartesian. Now, how do you know if you wrote something in Cartesian? You need x, y's, and z's, and no other symbols, right? No phi's, no thetas, no r's. Okay, so that's actually a check. So this is the Cartesian. But what about cylindrical? Okay, now that we need to think about. Now, if we're in cylindrical, what do we need? We need to have r, theta, and z. So the z, we don't need to do anything. We like that z. So we can't have the x and y. So we want to get rid of x and y's and replace them in terms of r and theta. But, again, going back to our formula sheet. What a great formula sheet. We get that r squared is x squared plus y squared. And we say, brilliant! Brilliant! So we're going to do a quick substitution. We're going to replace x squared plus y squared by r squared. And that'll give us our cylindrical. Okay, so that what we get is we get the following. R squared plus z minus 9 squared equals 81. And that's in cylindrical coordinates, because the only things showing up are things which correspond to cylindrical coordinates, r, z's, and thetas. And they might say, well, whoa, Steve, there's no theta. Totally fine. You don't need to use all the symbols. The key thing is not necessarily that you have all the symbols, but that you don't have any of the other symbols. That's what we mean when we say write it in the different coordinate systems. All right, so there was a lot of things you had to find, but they're all there. We're done. We did it. Woohoo! Yay us. So look at all these wonderful things. All right, so what did we get to do? Well, we got to do completing the square. Good times. And that's something that you often get tested on, especially when there's spheres involved. It's not too surprising that when you see a sphere involved, that you'll see it completing the square somewhere hiding. But also, again, more practice in switching coordinate systems and learning to be comfortable in the different coordinate systems. And that's important. We want to get comfortable. These are nice coordinate systems. We should get to know them. All right, well, let's keep moving along. Consider the circular cylinder defined by r squared sine squared theta, r squared cosine squared theta, 4r cosine theta, add all those together equals 5. Is the axis of the cylinder parallel to the x, y, or z axis? And it says give the radius of the cylinder and a point on its axis. Now, when we're talking about a circular cylinder, well, that means that we have something that could look something like this. But it could also be turned on its side. So maybe it looks something like this. Or maybe it looks something like this, right? It depends, which axes are we parallel to. So we have to figure that out. But we know we look like a tube of some sort. So how do we go about this? Well, there's a couple ways that we could do this. But I think that oftentimes when I'm not sure what to do, I say, let me get back to something I'm more comfortable with. It's a great strategy in math. It's sort of this idea of let's reduce it down to something that we know how to solve. So right now we see r's and thetas. And we say, oh, well, what's going on here? R's and thetas, where are the other symbols? Now, in particular, what's not here? Well, there's no x's, no y's, no rho's, no phi's. So this is supposed to be given to us here in cylindrical coordinates. Now, there's actually a really, really big hint that gives us the first one for free. If we did nothing else, we could answer the first question for free. What is missing from our formula if we put on our cylindrical coordinate colored glasses? What don't you see here? You don't see any z. Well, what does that tell us? Well, it tells us that regardless of which layer of z that we're on, we're going to have the same picture in terms of what's going on with the r's and the thetas. So it's like we're copying up and down z, which means that this is the right picture. It's got to be the z-axis. Now, we're going to go through and do this out in a little bit more detail, but here, again, we're taking advantage of the fact, hey, you forgot to mention something. But that's for this problem. Let's go through now and be a little bit more careful. Okay, so I'm going to rewrite this. R squared sine squared theta. Now, they chose to put in the sine squared theta. An interesting choice and maybe kind of a hint. So what if we thought about it in that way? As r sine theta quantity squared. And then this r squared cosine squared, r cosine theta quantity squared plus 4, and I'm going to write r cosine theta and equals 5. Now, what do we know? If we look on our formula sheet, we have some information. And of course, who doesn't check the formula sheet if they need information? We know that we have x equals r cosine theta and y equals r sine theta. So we say, everywhere we see r cosine theta, we can put x. Everywhere we see r sine theta, we can put y. And lo and behold, we have some nice things coming together. All right, so we have y squared plus x squared plus 4x equals 5. You might have noticed I left a suspicious gap because I saw x squared and 4x, and I'm like, we probably want to do some completing the square. And we say, okay, so what's going on? Well, what do we need to add? Take the middle term, divide by 2, square it. That's a 4, so we add 4, and we just do it to both sides, right? So that plus 4, this is coming from complete the square. So we added that to both sides. And now we say, okay, what do we have? Well, this becomes x plus 2 quantity squared, or if we reverse the order, just because that's the way we're more used to things, x plus 2 squared plus y squared equals 9, which is 3 squared. Okay, so what does this look like? In the xy plane, because we can think of it as just a circle in the xy plane. So in other words, as a two-dimensional shape, it says go over here to -2. So x is -2. And then have a radius of 3. So this is a circle. So the center is at -2, 0, and the radius is 3. Now, how do we think of it in a 3-dimensional picture? Well, okay, so what we do, we'll draw some axes here. So we have our x, y, z. So we move -2 over. So let's say that's -2. And in the xy plane, we have our circle. So this circle is here. And finally, as we mentioned, since there's no z dependence, we're just going to copy it straight up and straight down. So there's our shape. Okay. So finally, what do we do? Is the axis parallel to the z-axis? Well, the x, y, or z-axis. And we say cylinder parallel to the z-axis equation does not involve z. So that's the key. It's because we're missing that z in the equation. That tells us that, hey, if you move along that axis, it's always going to look the same, and that's what causes it to be parallel. Now, we're also told give a point on the axis. Now, not the z-axis, right? Where we mean the following. This is the axis of the cylinder. That's what we're after. So how do we find it? Well, we have that point. So where is that point? It's at -2, 0. So a point on the axis of the cylinder is at -2, 0, and here there's actually infinitely many points that work. So put in whatever number you like. So I like to stay simple, so I'm going to stay 0. 0 is very simple. But this last one could be arbitrary. It could be anything. So free choice. Who doesn't like a free choice? So it could have been 7, 100, pi, -2, 1. But 0 seems pretty simple, and who doesn't like simple things? All right, well, there you go. There you go. Kind of a different problem. Interesting ideas here. This idea of cylinders. And we'll talk a little bit more about this again in upcoming lectures. So much preview of things to come. It's fun. We're going to have a blast. All right, let's keep going. Find the volume V of the set of points x, y, z satisfy -4z is less than or equal to x squared plus y squared plus z squared is less than or equal to 2x plus 2y plus 34. And probably the first reaction is like, what? And like, okay. But our second reaction is like, let's think about this. Now, one thing is we have to sort of parse, what does this mean? Now, we see the word volume, so we say, okay, so there's sort of like a 3-dimensional shape coming into play. We're like, okay, so we kind of have to say, what is that 3-dimensional shape? And that's really the heart of the problem. How do you find this 3-dimensional shape? And it's given to us in terms of these inequalities. And note that there are 2 inequalities. So we're going to break this into 2 parts. So let's start with the first one. Okay, so here we go. Here's our step 1, the first inequality. So what do we have? Well, we have that -4z is less than or equal to x squared plus y squared plus z squared. Well, let's think about what we think it probably is. And well, we are all thinking the same thing. We see x squared, we see y squared, we see z squared. It's a sphere. You're right, it's a sphere. And so we want to try to figure out, well, which sphere is it? So we'll start by moving things around. So I'm going to move this negative 4z across so that I can put all my variables together. So x squared plus y squared plus z squared and plus 4z. So when it comes across, it'll come across as a plus 4z. They might have said, oh, Steve, you forgot your suspicious gap. Well, no, I left plenty of room for a suspicious gap there. Don't worry, I would never forget. I would never do that to us. Okay, so the x, y's were good to go. Z squared plus 4z, complete the square. And so if we do that, take the middle term, which is 4, divide by 2. Well, that's 2, square that, means we should add 4. So we're going to add 4, but if we do it to one side, we should do it to the other side. And we get the following. We get that this says that 4, which I'm going to write this as 2 squared, less than or equal to x squared plus y squared plus z plus 2 squared. And now we say, okay, how do we interpret this? Well, notice that we are greater than or equal to, and there's a sphere involved. If we think of this side as distance, because that's like the distance x, y, z to the center, the distance is greater than or equal to 2. So that means we want to be outside. So we want to be outside the sphere. And which sphere? Well, the sphere has center 0, 0, negative 2, and it has radius of 2. Okay, so that's the first thing. So this first inequality is saying, oh, you have to be outside a sphere. Now, we're going to do something very similar with the second, right? So the first inequality, just look at those two. Now we're going to look at those two. All right, so here we go. Similar process, and let's see what we get. Okay, so we have that x squared plus y squared plus z squared has to be less than or equal to 2x plus 2y plus 34. Okay, we're going to move things around. And similar process, x squared. We're going to move the 2x to be next to the x squared because we want to put variables together. We have y squared. Move the 2y to be next to that. And we have the z squared. And we'll leave the 34 on the other side. We run through the process of completing the square. Hopefully by now we're getting pretty good at it. Negative 2 divided by 2 is negative 1. If you square that, you get plus 1, which means you should add 1 here. But if we add 1 here, balance it out. Add 1 there. Same thing here. Negative 2 divided by 2 is negative 1. Squared is 1. So we should add 1 here. So we should add 1 there. And lo and behold, we get the following. We get x minus 1 squared plus y minus 1 squared plus z squared is less than or equal to 36, or 6 squared. All right, good. Now, let's parse this. We have an inequality again. So if we're thinking of this as distance, and again, that's distance to the center, our distance is less than or equal to what should be our radius. So we want to be inside. So we say, this is inside a sphere. And what sphere is it? Well, the center should be at 1, 1, 0, and the radius should be at 6. Okay, there we go. 2 spheres. So, what's the picture? And this time I'm going to be a little bit careful because I do want to make sure I get the picture right. Okay, so if we draw our picture here, the center being at 0, 0, minus 2 and radius 2 says you go down to, in the z direction, and you have a sphere here. So here's this sphere, radius 2. All right, and we want to be outside of it. And then, what else do we have? Well, we're going to go 1, 1. So here we have our sphere in the xy plane. The center is right there. And then we're going to go out quite a distance, actually. It's a very big sphere. And so we have that. So it's a sphere that's been sort of nudged over a little bit. Now, if we wanted to be a little bit careful, and we can be a little bit careful, we can talk about what's the distance between the centers. And so we'll make some notes here. Distance between centers. Well, we get the following. We have our distance would be square root of 1 squared plus 1 squared plus negative 2 squared. So negative 2 squared, which if you work that out, that's square root of 6. Now, how big is square root of 6? It's somewhere between 2 and 3. So that means that certainly we're less than 3 apart from each other. What's all that trying to say? It's trying to say that the small sphere is inside the big sphere. And we want to be outside the small sphere and inside the big sphere. And so our great aha is, lo and behold, our volume is that shape. Like it's a big sphere, subtract a little sphere. So the volume is the volume between the two spheres. So is big sphere minus little sphere. All right. Now, do we know the volumes of a sphere? Yes. And if you look on the formula sheet will say it this way, volume, and then it has a little cute little picture. It's like, hey, look at that adorable picture. That's 4/3 pi r cubed. Okay, so what do we get? That's 4/3 pi. What's our big radius? 6. So 6 cubed. Minus 4/3 pi times our small radius. So that's 2 cubed. And that's an answer. Perfectly fine answer. Nothing wrong with that. Now, if you wanted to, you could, of course, work a little bit on it and simplify it. So, all right, at the danger of making mistakes, I'll probably say this is a fine answer, and it truly is. This is a perfectly fine answer. But the idea is take the big sphere, subtract the little sphere, and mostly it comes down to understanding what do these relationships say. Now, if you want to go further, 6 cubed, that's 216. 2 cubed is 8. 216 subtract 8 is 208. 208 times 4 is 832, so you get 832 pi over 3. But we're okay just saying it's this minus that. All right, good, right? Let's take advantage. It didn't say simplify as much as possible, and so we will not do that. All right, good. All right, and I will say about the only way that this could even make sense is to have one sphere inside the other. If they were overlapping on their boundaries, hopeless. For now, we'll get there eventually. All right, good. Let's keep moving along. Find the unit vector u from the center of the sphere, given by x squared plus y squared plus z squared equals 16y minus 8z plus 6x plus 27, towards the midpoint of the line segment connecting the point A, 9, 8, negative 3, and the point B, 1, negative 4, 13. All right. So there's a lot of things going on here. So it's not really a big problem. It's a collection of small problems that we have to work out along the way. And we have a little bit of choice in how we go about doing this. So I'm going to start with the midpoint part. So the midpoint, what is that? Well, if you see the word, you can kind of guess. Mid kind of sounds like middle, and point is a point. So it's the middle point. So you can imagine that I had point A and B. So here's 9, 8, -3. And here is the point 1, -4, and 13. All right, so I have that point. And, well, I should say I have these 2 points. And now I want the midpoint. It's the point that's midway between. So this is the midpoint. And, well, okay. How do we find it? Well, the good thing is that there's actually a very clean formula, which says you add the x entries together, divide by 2. You add the y entries together, divide by 2. And you add the z entries together, and you divide by 2. So 9 plus 1 divided by 2 is 5. 8 minus 4 divided by 2. Now, it's not really 8 minus 4, it's 8 plus -4. Okay, 8 minus 4 divided by 2 is 2. And finally, -3 plus 13 is 10, divided by 2 is 5. So our midpoint is 5, 2, 5. Okay, so that's one of our points. Okay, now let's find the center of the sphere. Okay, so that's our next stage. Okay, center of the sphere. All right. This is going to give us more practice with completing the square. Yes, this is definitely going to be completing the square practice for the next couple minutes here. So we're going to rewrite this by saying let's put things together. And we're going to be careful, right? Notice they went x, y, z. Here they went y, z, x. Oh, they can do stuff like that. So we're going to be careful. X squared minus the 6x, right? Because the 6x, that's there. Y squared minus 16y. Z squared plus 8z. All that equals 27. And notice we leave ourselves some gaps so that we can go through and do completing the square. And now, one by one, complete the square. First term, -6 divided by 2 is -3. Square that, add 9. And you would add 9 over here. -16 divided by 2 is -8. Square that, you add 64. So we'll add 64 there. 8 divided by 2 is 4. Square that gives you 16. So add 16 there. And what do we have? Well, 27 plus 9, that's 36. 64 plus 16, that's 80. And, okay, 80 plus 36 is 116. And you might be saying to yourself, that does not seem like a very good number. It doesn't have to be, because we don't really care about the radius, right? What do we care about? The center. That's what we care about. So this radius can be unpleasant. And 116 is unpleasant insofar as it doesn't have a nice square root. That's okay. That's okay. No problems for us. So, okay, x minus 3 squared plus y minus 4 squared plus, and then this will be z plus 4 squared equals 116. So our center is where? Well, x is 3, y is 4, and z is, whoops. Why did I write y minus 4? It's y minus 8. I am so sorry about that. Double check. Because I was like, wait a second, these can't give the same point. Yeah, they can't, because they were off. All right. Double check your work. As the great philosophers have said, you should check yourself before you wreck yourself. All right, so good news. We found the midpoint. We found the center of the sphere. We don't need to worry about the radius. That's not the problem. Now what do we do? Well, the next step is to say, hey, we're after a unit vector between those 2 points. Let's just find a vector. So a vector from the center, and that's 3, 8, -4, to the midpoint, and that's 5, 2, 5, is what? Well, how did we change? We started at 3, we got to 5, take the difference. 5 minus 3, 2. Went from 8 to 2, so that says take 2 minus 8, -6. And we went from -4 to 5. 5 subtract -4 makes 9. 2, -6, 9. Now, is this our answer? No, it's not our answer. Ah, dang it, but why not? What's wrong with this? What needs to be fixed? Well, there's a very important word, and we have to respect it. It's the word unit. It's not that we want to have a vector, it's we want to have the unit vector. So we say, okay, we have the right vector insofar as direction. Okay, so this is good, has the right direction, but has the wrong length, because that does not look like a vector with length 1. So we need to fix it. So to fix, we're going to scale it down. Because we like the direction, we just need to scale it so its length is 1. So our next step is, what's the magnitude of this vector? Okay, so the magnitude of 2, -6, 9, it looks a lot like the distance formula, because at its heart, it's really the distance from the start, the tail to the head of the arrow. So we'll take 2 squared, -6 squared, 9 squared. That's the square root of 4 plus 36 plus 81. 4 plus 36 is 40. Add 81. That's 121. And it turns out that's actually a nice number. That's 11. So currently this vector has length 11. We want to have length 1. So we say, okay, the last thing, and this is our last step, is we're going to take our vector and scale it down, shrink it. So our desired vector, u, is 1 over this length, so 1/11 times 2, -6, 9. And that's our answer. Nice, nice. So there were a lot of little steps along the way, which meant, of course, lots of little places to make mistakes, and no individual one is too bad, but of course, oftentimes those can be the hardest ones to do because it means lots of small chances for mistakes. So let's recap. What happened? We had the 2 points, so we said, hey, we can get the midpoint. Nice. It's like an average of the points. Technically, that's not what it is, but like it. And then we said, okay, we need the center of the sphere. So we moved things around and we did completing the square. We found the center. We didn't need to worry about the radius because that doesn't come into play. So don't worry if the radius turned out to be a not nice number. Now that we have the 2 points, we can find a vector that goes between them. Now that's the vector that connects the 2 points, but we said, hey, we want to have a unit vector that points in that direction. So we say, okay, well, we don't want to take the vector exactly between those 2 points. We got to scale back. Now to know how much we need to scale by, we need to find the length of the vector. And once we knew the length of the vector, we knew how much to scale by, which gave us our final answer, the unit vector pointing in the right direction. Whew. All right, and there we go. There we go. Take your time, pace yourself. All of these are things you can do. And you're going to be great. Find the volume of the solid described by the inequalities 3r is less than or equal to z is less than or equal to 6 plus square root 4 minus r squared. All right. Now, there's a couple of things that we see going on here. We see the word volume. And we say, okay, volume is like a three-dimensional thing. Okay, so we know we're in 3 dimensions. We also see r's and z's. Now, what does that tell us when we see r's and z's? It tells us we're in cylindrical coordinates. Okay, so we're going to put on our cylindrical coordinates hat. Okay, so put on our cylindrical coordinates hat. And one other thing we might say is, hey, you know, what don't we see? Well, there's no theta involved. Now, what does that mean if we don't see a theta involved in a formula with cylindrical coordinates? Well, that tells us the following. That tells us that there's symmetry around the z-axis. In other words, we can spin. And say, okay, cool. So when I say there's symmetry around the z-axis, we're spinning, right? So how do we figure out what our shape is that we have to find the volume of? Well, what we can do is let's start in what I like to call the RZ plane. So we're going to have the RZ plane. Okay, so work in the RZ plane. All right, so these are all notes I'm making to myself. And let's start. We have some inequalities here. So I'm going to say let's pick an inequality. So let's pick this inequality. 3r less than or equal to z. So we have 3r less than or equal to z. And we're in the RZ plane. Another way to think about this is, well, think of this as z is greater than or equal to 3r, right? That's just another way of saying that. So if you wrote z equals 3r, and if you were to plot, now you might say, well, I'm not comfortable with r's and z's. Think about it in terms of y's and x's. If I said y equals 3x, it's like, oh yeah, that's that steep line. Same idea. So it's like, okay, so we have this line coming up. So this is z equals 3r. And we say what? Well, we want to be above that, right? We want z to be greater than or equal to 3r. And so we are going to be up here. Now, I should mention that when you work in the RZ plane, you only work in what I like to call the right half of the RZ plane, right? You don't work over here. We don't work with negative values for r. All right, so that's part of our picture. Now, what's the other part of our picture? Well, we have that other inequality we have to talk about. This z is less than or equal to 6 plus the square root of 4 minus r squared. So z less than or equal to 6 plus the square root 4 minus r squared. Now, this one we probably should think a little bit about, because I don't think it's going to be a quick like, aha, this is clearly this. Like no, we got to think about it. If you rewrite this, let's do the equality first. So z is equal to that, so that says z minus 6 equals the square root 4 minus r squared, or z minus 6 squared equals 4 minus r squared, or r squared plus z minus 6 squared equals 4. Okay, with that in mind, what is it saying? Well, it says it looks like a circle. if you can't quite see that, put in X's and Y's. You're like, oh, it's a circle, right? Yeah, it's a circle. X's and Y's are symbols. R's and Z's are symbols. And symbols can be changed. That's okay. It's okay. And where would it be? Well, you come up here. Let's say this is 6 here. And actually, in the interest of space, because let's put 6 here. Radius of 2, right? 4 is 2 squared, so we're going to go up 6. R and Z equals 6, R equals 0. And then it would be a radius 2, right? That's what this would draw. But go backwards, right? What do we have? Well, because when we go backwards, when you came here, you kept the positive part of the square root. It's actually going to be the top half of your sphere. So this is your Z equals 6 plus the square root of 4 minus R squared, is this piece right here. It doesn't make sense for larger values for R, so it stops at R equals 2. Because if you put in something bigger than 2, you get a square root of a negative number. And so we're told we need to be less than or equal to that, which means we've got to be below that part. Okay, so we're below that part. Now, we do our great cross your eyes and look at the overlap, and that'll tell us what's going on. And lo and behold, if we came over to the same place at 2 and we went up, where would we hit? We would hit at 6. So these are perfectly aligned to do the following. So here we're going to have our half circle, 6, 8. I said half circle, it's even just a quarter circle. We come down, we come up. All right, so this is a quarter circle. And here we have a line. And that is their overlap. That's where we satisfy both inequalities. All right, now this is the RZ plane. How do we get the shape? Because this is a two-dimensional thing, right? We need to get to 3 dimensions. Now we take advantage. When we talk about the RZ plane, we're just sort of saying, well, what happens if you look at a slice down the z-axis? So this is the z-axis here. So now what we're going to do is we're going to spin this, which is to say the following. What do we have going on? Well, in 3-dimensional space, this part right here, this is the z-axis, that matches here. And so what we'll see is we'll see this part coming out, right? This is, but then you spin it, and we say, okay, great. What do we have? Well, now we say, oh, this is a hemisphere, because when you spin that quarter circle, you're going to make the top half of a sphere, and then this bottom half, this triangle, when you spin it, makes a cone. And so we have 2 pieces. All right, so now our great, do we know how to find these volumes? Well, yeah, we can find that because we have additional information. Not only do we know it's a cone and a hemisphere, but we know things such as the measurements. So for this hemisphere, what's the radius? So for the hemisphere, we have a radius of 2. For the cone, what's the radius? That's this length across. That's also 2. What's the height? Well, the height is 6, right? This is the height. So radius, height. And now we look in the formula sheet. The formula sheet. What a wonderful tool that is. We say, well, do we know how to find these things? And we do. we have the following information. So all of this was to help us understand what's going on with our shape. We are told that the volume of a whole sphere is 4/3 pi r cubed, and we're told that the volume of a cone is equal to 1/3 pi r squared h. So now we're going to add these two volumes together. So what do we get? Our volume, well, it's a hemisphere, so it's going to be 1/2. So 1/2, this 1/2 is because it's half a sphere of 4/3 pi r cubed, 2 cubed. And now we're going to add to that the volume of the cone. So plus. Okay, and what's the volume of our cone? That's going to be 1/3 pi. Our r is 2, so 2 squared, and our h is 6. 6. Okay. Now, that's our answer. We can clean it up a little bit. We can get a 2 to cancel, so that'll help. And so what can we do here? This can be written as, we can factor a 4/3 pi out, 4/3 pi. So that takes care of the 4, the thirds, and the pi. What's left? Well, I have a 2 squared, which is 4. Now here, I factored out a 4/3 pi, so that means I have a 6 left. 4 plus 6 makes 10, so that gives us 40/3 pi. And that's our answer. Now, could you have stopped here? Yes. Yes. It didn't say simplify as much as possible. I know some of you are simplifying junkies and like, I'm going to simplify. That's my right. You know, and that is your right. You can simplify if you want, but be careful. Sometimes people in the process of simplifying introduce errors and lose a point. And we want all the points. So simplify if you're confident, but if you're not, it's okay at this stage. As long as you're following the instructions, you're good to go. All right, let's keep going forward. Let z equal the vector, because we see these angled brackets, 9, 1, 6. Find scalars a, b, and c such that z is a times u, b times v, and c times w all add together. If u is the vector 2, 3, 1, v is the vector 2, minus 1, 1, and w is the vector 1, 2, minus 1. What? Okay, so we're after a, b, and c. So we're solving for a, b, and c. So let's start by writing out what this says. We know what z is. We know what u, v, and w are. So we're told that 9, 1, 6 is equal to a times 2, 3, 1 plus b times 2 minus 1, 1 plus c times 1, 2 minus 1. And just to remind ourselves, where is all this coming from? Well, this is just saying that z is a times u plus b times v plus c times w. All right, now what can we do? Well, notice here we're scaling and adding. So what we can do is we can take that right-hand side and just sort of put into one big vector. One vector that combines all these pieces together. So if we do that, we get the following. We get, well, this is going to be 2a, then 2b, and c, comma. So that's the first entry. 3a minus b, 2c. That's the second entry. A plus B and minus C. And that's the third entry. All right. So now we have all of our pieces. And we say, okay, well, two vectors are equal to each other if and only if they're equal entry by entry. And we say, oh, well, that gives us three equations, right? So this 2a plus 2b plus c has to equal 9. This 3a minus b plus 2c has to be 1. And this a plus b minus c has to be 6. Okay, so what we're going to do is we're going to get down to the following. 3 equations, 3 unknowns. All right, so writing it, we have 2a plus 2b plus c equals 9. 3a minus b plus 2c equals 1. A plus b minus c equals 6. All right, now how do we solve something like this? Well, what we do is we sort of put on our hat that says, we'd like a simpler problem. And that's really what you do on these. So you say 3 equations, 3 unknowns. You don't have to make the sound. But it's like, if I could make it 2 equations, 2 unknowns, that would be even better. Even best is 1 equation, 1 unknown. I'm really good with that. And so that's where we're going to head. So what we're trying to do is trying to eliminate variables. So at this point, it pays to sort of look at this and say, can I combine these equations in nice ways to help knock something out? And if you can knock 2 things out in one step, that's even better. And so looking at these, you can compare the first and the second, first and the third, second and third. But notice how the first and the third draw the I. Because you see, 2a, a, 2b, b. So this is like double and double, but this one's not. So idea. So we're going to do the sort of, this is kind of like matrices and elimination, but essentially you should think of it as elimination. That's the mindset. Oh my gosh, good times, right? So here's what we'll do. We're going to multiply the third equation by -2 and add the first equation. And we're just going to put these two together. Ignoring the middle one for the time being. Don't worry, it will get its time to shine. Why do that? Well, our goal is to knock things out. 2a minus 2a gets us 0 a's, right? Because the a's will cancel, 2a minus 2a. 2b minus 2b is not to be. It's going to be 0 b's. The b's will cancel. Then a c minus 2 times minus c makes c plus 2c. That makes 3c. On the other hand, we have 9, right? 1 times 9. Don't forget this. Whatever you're scaling by goes through everywhere. And minus 2 times 6. Well, that's going to become 9 minus 12, which is -3. And so, well, since those are gone, lo and behold, now we have C. We're a third of the way done. Woohoo! Yay, us. And because we have C, we can use that. So now that we have C, and I should comment, you will not always be able to knock out 2 at the same time, but hopefully you have nice math instructors and that'll happen. And so fingers crossed. Please be nice, be nice. If not, just chip away, and the goal is simplify, simplify, simplify. Keep knocking things out. All right, so let's update with what we have. And because we used the first and the third, I'm just going to focus on the first and the second here. So we get that 2a plus 2b plus c, which is really a plus and negative 1, equals 9. And here we'll get 3a and minus b plus 2c makes a minus 2 equals 1. Now we can do some various things. I can add 1 to both sides in the first equation. Everything would then be even. So if we add 1, then divide by 2, we'd get a plus b equals 5. Yes, it's true. I did 2 steps at one side, and I know that's dangerous, but I know we can do this, right? Add 1, so you have 10 divided by 2. Down here, well, no fancy dividing, but we'll add 2, and we'll get 3. Now, what can we do here? Well, we want to cancel. Look at those b's. It's just like they're asking us to say, look, we're ready. We're ready to get canceled. And we're like, okay, we'll accommodate you. We will help you in your journey to get canceled. And so what do? We can add these two together. We don't even have to use a scaling factor. A plus 3a makes 4a. B minus b makes 0 b's. And 5 plus 3 makes 8. Of course, we don't need to worry about the b's. 4a equals 8. So that says, oh, hey, a needs to be 2. Now, once we know a equals 2, we can put that in. And we can just need to use just one of our equations. So let's go ahead and use our first equation here. And what do we get? Well, we get 2 plus b equals 5. Okay, well, I think we can solve that one. Yes, b equals 3. And there we go. We solve for a, b, c. You don't have to solve for them in order, but let's put them all together. Be nice to our grader, right? We want our grader to make sure they can easily check our answer. So we can do a equals 2, b equals 3, c equals negative 1. Put them all together. There you go. And life is good. Now, sometimes you might want to say, I'm a little bit skeptical. I may have made an algebra mistake. I know. I have been there many times. So, can you check your work? Well, you certainly can redo everything, but you can also just sort of plug things in and just see if it works. Like 2 times 2 is 4, plus 2 times 3, that's 6 more, so that's up to 10, plus a negative 1 makes 9. 3 times 2 is 6, minus 3 makes 3, minus 2 more makes 1. Then we have a 2 plus 3 minus 1 is a plus 1. 2 plus 3 plus 1 is 6. So we've verified that it satisfies the original, which means we definitely got it right. So this problem is, once you understand, oh, it's just a matter of 3 equations, 3 unknowns, then you're like, woohoo, it's 3 equations, 3 unknowns. And they're like, oh, it's 3 equations, 3 unknowns. You know, there's a roller coaster of emotions. But it's not so bad. It's just a matter of set up your equations, then start looking for good cancellation, and chip away. There's oftentimes lots of ways to solve it, and mostly just a matter of be careful, be methodical, make sure to distribute any scaling factors that you use so that you don't lose anything. But there you go. All right, let's move along. The parameterization x equals 2t plus 1, y equals 3t minus 2, and z equals t plus 3 defines a line in 3-dimensional space. Okay, all right. That's a typo. That's okay. We love our instructors. We'll forgive them for a typo. Space. Find the point on this line that lies closest to the point 4, 1, negative 5. Now, this is sort of, in some sense, a preview of things to come. But what's sort of the picture that we have in mind? Well, we're in 3-dimensional space. We're told that there's this parameterization, that's a line. And so if you think about what that means, the parameter just means that there's a variable. In that case, the variable is t. So we're writing things in terms of t. And if you plug in a value for t, you get an x, y, z. Plug in a different value for t, you get a different x, y, z. Plug in an even differenter value, more different, differenter. Anyways, you get another point. So the idea is, as you plug in all of those values for t that are possible, you get a line. So there's the line. On the other hand, we have some point, and now the question is, all right, among all the things along the line, there's lots of points I could have picked. Which one is closest? We will come back to this type of problem when we have more tools and see that there's wonderful geometric ways to do this. We haven't quite built up our geometric toolkit yet. So with that in mind, we'll say, well, let's not dig into our geometric toolkit. Let's dig into our calculus toolkit. Because there's a certain part of this problem that says there's a calculus type thing going on. And the certain thing that suggests a calculus type thing is this notion of est. In other words, we're trying to find the best. And when you see things with an est attached to them, what you're really thinking is, oh, we're doing optimization. And so with that in mind, we'll put on our optimization hats. So what's our idea? So we look at this and we say, okay, we're going to optimize. Now, what is it we're trying to optimize? Well, we're going to have the one that's close. So that means we're going to optimize distance. So that's our goal. That's our thought process looking at this problem. All right, so let's write this down. So our distance from a point x, y, z to that point 4, 1, negative 5, well, for right now, it's the square root of x minus 4 quantity squared plus y minus 1 quantity squared plus z minus 5, so that's z plus 5 quantity squared. However, there's a couple of things. This is an arbitrary xyz. We don't want an arbitrary xyz. We want an xyz on the line. Okay, so how do we get an xyz on the line? Well, we can replace x, y, and z by these formulas. Where we see an x, put 2t plus 1. Where we see y, put 3t minus 2. And where we see a z, put a t plus 3. But there's another issue, which is probably going to be more distressing. Well, okay, well, let's do that one first, and then we'll talk about our more distressing part. So we have 2t plus 1 minus 4 quantity squared plus 3t minus 2 minus 1 quantity squared plus t plus 3 plus 5 quantity squared. Okay, we'll clean that up. The square root, that's the other thing. But here's a great idea. And we probably have used it before. I know we've talked about it before in some of our earlier calculus courses, which is to say, if I want to make the square root of something big or small, I just need to make the inside big or small. So we have an update to our thought. Let's optimize not distance, but distance squared. Okay, so then our distance squared becomes, and now we can get rid of the square root, and we'll clean up the inside. So 2t plus 1 minus 4 becomes 2t minus 3 squared. 3t subtract 2 subtract 1 will become 3t minus 3 quantity squared. And our t plus 3 and subtract negative 5, now that's going to become our t plus 8 quantity squared. Okay, so that's what we need to make the best. We're trying to make that as small as possible. So how do you make things small? Take a derivative. So we're going to take the derivative with respect to t. So we'll come down here. Taking the derivative of the first term, the 2 comes down. 2t minus 3. And don't forget the chain rule. Chain rule. It's the best rule. It's the chain rule. Okay, so derivative of the inside, 2. Plus, go to the next term. The 2 comes down. 3t minus 3 times derivative of the inside, which is 3. And then plus, the 2 comes down. T plus 8 times derivative of the inside, which is 1. All right, now that's the derivative. What do you do with your derivative if you're trying to optimize? Set it equal to 0. Now we can do something really quick, which is cancel all the 2's right away, since every term has a factor of 2. So, what do we now have? Well, if we distribute here, we get 4t minus 6 plus, distribute here, 9t minus 9 and plus t plus 8 equals 0. So we have a 4t, a 9t, and a t. If we put those together, their t-ness combined, 14t. Minus 6 minus 9, that's minus 15. Add 8 makes minus 7 equals 0. Or 14t equals 7, or t equals 7/14, also known as 1/2. Now, is this our answer? And why not? It's not our answer. What? Dang it! I thought we were so close, right? Because make sure you answer it in the way that it was asked. It didn't say find the value of t. It says find the point. And that's our answer. Our answer needs to be a point. Okay, so find the point. What have we found? We have found the value of t where that point is closest. So how do we finish? Well, from here, we're going to plug this t into the line. All right, so what do we end up with? Well, we're going to end up with x is 2 times 1/2 plus 1. Well, okay, 2 times 1/2 plus 1, also known as 2. Y is 3 times 1/2 minus 2, so that's 3/2 minus 4/2, that's negative 1/2. And z is 1/2 plus 3. 3 is also known as 6/2, so that makes 7/2. So our point would be at 2, negative 1/2, 7/2. And that is the answer. 2, negative 1/2, and 7/2. And there we go. And there we go. And as I said, we'll come back to this type of problem and be able to do it in different ways geometrically in the near future, but that's a story for another time. And that does it for this, our last problem on this practice quiz. Many fun things were done. Thank you for coming. Thank you for putting in the time, the effort, the energy, and for working hard. I'm glad you're investing in yourself. You're definitely worth it. I hope you have a great quiz, a great week, and let's see each other again. All right. Bye.